So in this video, we're going to continue talking about wave characteristics of light. So we've already talked about reflection and looked at mirrors and how to draw wave diagrams for mirrors. And now I'm going to talk about lenses and transmission and a little bit of an introduction to refraction. So light is transmitted through transparent materials like glass, and in particular, we're going to talk about lenses here. So when light passes into a new medium, it actually slows down, and I will go into more detail about refraction in a later topic, but we gotta know the basics of refraction, or the basic idea of refraction, in order to understand how a lens functions. So light, we said, travels in a vacuum at 3 times 10 to the 8th meters per second, and it travels about that velocity in air as well. But when it encounters a dense medium like glass or water or oil, something like that, it actually enters into that new medium and it slows down, and as a result it bends or refracts through that medium. So for now, just know that, and then we'll continue more talking about refraction later and actually performing some of these calculations and talking about index of refraction. Now, this also is how a prism works. So we know that white light is actually a combination of all the different colors of the rainbow. So red, orange, yellow, green, blue, indigo, and violet. And so when we see a rainbow, it's because light is being split as it passes through water droplets that are acting somewhat like a prism. So you can see here this example of white light entering into the prism, and you can see as it enters, based on the color of the wave, which relates to both its energy, its frequency, and its wavelength, it's going to bend in that new medium, and then when it strikes the other surface, it strikes at a different position, and that's what generates the rainbow. So something about the wavelength of light also contributes to the amount of refraction, but we'll get to that later as well. So what I want to talk about now is, in particular, lenses, and lenses transmitting images and creating, or transmitting images and creating an image at a certain location. So lenses form images by refracting light instead of reflecting it. So refraction, like I just said, is when light bends when it passes through a material. There are 2 different kinds of lenses. There's either converging lenses or diverging lenses. If we look at a converging lens, you can see here when light travels through or encounters the lens, it bends the light rays in and they converge on the opposite side. Whereas a diverging lens is sort of bowed out like this, so as light strikes it, it actually bends outwards and it diverges on the other side. Now, it's important to note that when we looked at mirrors, there was only one focal point, because light was always bouncing off one side and reflecting back into that side. Whereas when we talk about lenses, the light could come from either end. So there's a focal point here, but there's also a focal point on the other side. So the same for a diverging lens, there's a focal point here, but there's also a focal point on the other side if light were to come through the other side or be transmitted through the other side of the lens. Now, what's nice about the lens equation about ray diagrams is that for a majority of the rules, they're all the same. There are only slight differences that we have to know about lenses from what we've already learned and done with mirrors. So you have the same ray diagram rules and the same equation, but there's a little bit of difference. So the things that are the same as the equation, so 1 over s image plus 1 over s object, or the position of the image in the object, is equal to 1 over the focal length. The rules for the ray diagrams are the same. The first ray goes from the object parallel to the principal axis and through F. So from the object, so here's my object, parallel to the principal axis, encounters, this is the lens here, and through F. The second is from the object through F and then parallel to the principal axis. So this goes from the object through F and then parallel, and then the first goes through C and back. So let's talk about what the actual differences are. Well, lenses, like I said, have 2 focal points because they go because light could go through either side, and you have to use both focal points when drawing the ray diagram. So we always start by doing the first ray and decide, all right, am I converging or diverging? And that determines what the focal point is that I use. So this would be a converging lens. So the first ray goes parallel, and as I strike the mirror, it's going to converge, so it's going to bend the light in. So I would use this focal point first, and then I'd use the other focal point for the second ray. Oppositely, if it was a diverging lens, then as the light came here and struck the surface, now it's going to want to diverge and go this way. So we'd use this focal point first, and then we'd use this focal point for the second ray. The next thing that is the difference is where C is. C is in the middle of the lens. So it's right here, sort of at the origin between the principal axis and where the lens crosses it. Now, if we look over here on this side, another difference that we need to think about is the fact that lenses naturally transmit light, right? So a real image is going to appear on the other side. Unlike a mirror, mirrors reflect light, so a real image was over here. So just a few slight differences to remember when doing mirrors versus lenses, and we'll practice a bunch of ray diagrams. So here you can actually see for diverging lenses what ends up happening. So here the first ray goes from the object parallel to the principal axis, and then as it counters the lens, it's going to diverge up this way. So we're going to use this focal point first, and then the second time we're going to use this focal point. So the second ray goes through F and then parallel to the principal axis. So you can see here, ray 2 looks like it's going to go through F, but as soon as it encounters lens, it's going to diverge and go parallel. And then the last one is through C and back. So we can see that it creates a virtual image that's on the same side as the object. We're using both the Fs. Now note here it says that mathematically when we use diverging lenses, F is negative. When we do converging lenses, mathematically C would be positive, right? Magnification is the same. We use the same exact equation. Image distance over object distance will give us magnification. And remember, I said all of the conventions that we can memorize are right here. So if you can memorize this table, then we can use these rules for every single problem that we're looking at for mirrors and lenses. So for both mirrors and lenses, if M is positive, it's upright. If M is negative, it's inverted. For both mirrors and lenses, if SI is positive, then it's real. If the image distance is negative, it's virtual. For concave mirrors and converging lenses, we always make the focal length positive, and for convex mirrors and diverging lenses, we make the focal point negative. Okay, and then remembering this idea that mirrors reflect light, so a real image is in front of the mirror. Lenses transmit light, so a real image is behind the mirror. It will be a lot easier to memorize what is here on this table in your ray diagram rules than it is to remember conventions for different scenarios. So go ahead and work on ray diagrams for different things and using these conventions to define all mirrors and all lens images and objects.